Hello, welcome to the lecture series on control systems engineering. In this session, let us discuss about state models. Under this, we will discuss or we'll learn how to develop state models, how to determine system response. Then we'll analyze the state models for controllability and observability. Okay, you can watch this video to be very useful and helpful. Okay, first thing is, what is this state space theory or state space technique? Or sometimes we call it a state variable theory also. Or they call it as modern control theory. So far, whatever we studied is called classical control theory. And this is known as modern control theory. What is the difference between what we have studied so far and what we are going to study now? Classical control theory, you have very clearly observed, it is a transfer function approach. Modern control theory is direct time domain approach. So we don't take Laplace, go to S-plane, again split into partial fractions, take inverse Laplace. All such things are not there. Our theory was restricted, like in our study, to linear time invariant systems. Here, any type of system can be studied using this theory. And also you must have observed all our problems had single input, single output. In the beginning only I had told you it is a CISO system, single input, single output problem. Here it is multiple input, multiple output problems can also be handled. Single feedback, any number of feedbacks you can use. So we use methods like Polar, Nyquist, Bode. All these are all approximate methods. Here we follow exact methods. Computerization is difficult, computerization is easy. Even for this now, softwares are available anyway. This may not be exactly correct, but these are all the points, right? That makes the difference. What do you mean by state variables? The behavior of dynamic systems can be explained by means of differential equations. And that's what we have done so far. And the dependent variables of these differential equations are known as state variables. So in transfer function approach theory also we were concerned about dependent variables, which we called it as output. Assume that a control system is characterized by a differential equation like this. This is a dependent variable. This we call it as state variable. So that means to say, if you take a mechanical system in a differential equation, you will have displacement, dependent variable, velocity, acceleration. If you take electric circuit voltage, current, these are all the variables. Such variables we call them as state variables. What is state then? Is the minimum number of state variables required to completely describe a system on coordinate system. Okay, suppose I want to find what is the state of the system. If I know these coordinates, values of these coordinates, then I can represent the state of the system. Okay, so suppose it's a two coordinate system, then there are two coordinates, two variables are required. And a three-dimensional space, three coordinates are required. Of course, in a four-dimensional place, along with these three coordinates, probably you have another coordinate. So then fourth dimension. So if there are n state variables, then I require n coordinate systems. What exactly we do here in the state variable method? For us, physical system will be given. We need to write the differential equation of that dynamic system using the basic laws governing the system. We might get an nth order differential equation. We have to reduce into n first order differential equations. Then the dependent variable of each first order differential equation is a state variable, and each first order differential equation is known as state equation. Okay, dependent variable is known as state variable. So nth order differential equation will have n first order differential equations, means there will be n state variables. Then these whatever state equations we get, let us express them in vector matrix form. That vector matrix form we call it as state model. Then we solve the state model and obtain the state response for the given input. State response. This is what exactly I am going to deal under this topic. Okay. So let us understand the meaning of state variables with an example. So I have considered a spring mass damper system. Many times we have come across this. I do not have to draw the free body diagram and write the differential equation. By this time we must be familiar with the differential equation. So the differential equation is md square y by dt square plus f dy by dt plus ky is equal to f of t. This is the differential equation. It's a second order differential equation, correct? Second order differential equation. As per the procedure, I have to reduce into two first order differential equations. For that, let me call y equal to x1 and y dot equal to x2. There are two second order, so choose like this: y equal to x1, y dot equal to x2. I'll tell you what these x1, x2 are. So now you take this y dot equal to x2. Y dot is nothing but dy by dt is equal to x2. You know the d by dt part you represent by capital D. So capital dy is equal to x2. So y is nothing but x1, bring that x1. So it is dx1 equal to x2. Okay, right. Next, take the original differential equation. Keep d square y by dt square on the left and transfer everything to the right. And divide throughout by m. This I can write as d by dt of dy by dt minus k by m y, this one, then minus f by m dy by dt plus f of t by m. D by dt, let me call it as capital D. Dy by dt, I'll call it as y dot. Minus k by m, y is nothing but x1. Minus f by m dy by dt is y dot plus f of t by m. So y dot is nothing but x2. Minus k by m, y is nothing but x1. That is already written. Y dot is x2, f of t by m. Okay, this is another first order differential equation. Here I have one first order differential equation. So these equations are known as state equations. These equations are known as state equations. Now in these x1 and x2 are the dependent variables of this equation. So you can call them as state variables. If you see x1 is nothing but displacement and x2 is nothing but velocity of the spring mass damper system. So these are called state variables. So now you have understood the meaning of state variables and state equations. What is state space? If the state variables are the coordinates of a spatial system, then it is known as state space. Suppose I want to study the state. So I call this as say x1, this I call it as x2. So state variables are the coordinates. This I can call it as state space. State vector. A state vector is nothing but a vectorial addition of its state variables. Suppose you have nth order system, n state variables are there. I'll arrange them in the column matrix. Call it as capital X. I call this as state vector. Suppose there are number of inputs u1, u2, u3, u4, un like this, then I call it as input vector. Similarly, a number of outputs are there y1, y2, y3, etc. yn, then I call that as output vector. So a state model is represented by dx is equal to ax plus bu, y equal to ctx. Right, here x is state vector, u is input vector, y is output vector. You know, this is A is a matrix, B is a matrix, C transpose is a matrix. Correct. So this involves only state vector elements, input vector elements, right? Output matrix it is, right? So I will explain that, how to do that one. Sometimes state model is also represented like this. dx is equal to ax plus bu then y is equal to C transpose x plus du. This is more generic representation. This is for a linear time invariant system. Remember this, for the LTI system. As I said, x is the state vector, y is the output vector, u is the input vector, A is state matrix, B is input matrix, C transpose is output matrix. This D we call it as feed through or feed forward matrix. This is called feed forward matrix. Okay. In case where the system model does not have a direct feed through, then D is the zero matrix. Okay. So this is a generic form. So many times the problems which we handled, this will be zero. So that's why I represent it as dx is equal to ax plus bu, y equal to c transpose x. This is for linear time invariant system. If it is a time variant system, then matrix A will become function of t, B will also become function of t, C will also become function of t and D will also become function of t. Then time variant system. Okay, now anyway we are talking about LTI system, so we do not have to really bother too much about it. Now, having known what is a state model, let us represent or obtain the state model for a given system. Again, I have taken my favorite spring mass damper system, written the differential equation. I have chosen the state variables. Then I take this. Then you know that dy by dt is equal to x, d by dt is capital D, y equal to x2, y is equal to x1, so dx1 equal to x2. You got your one state equation. Again, I'll take this one. I'll write the second state equation, which is like this. Now, let us write the state model form. Our first equation is dx1 is equal to x2. Second equation is dx2 is equal to minus k by m x1 minus f by m x2 plus f of t by m. Okay. So first what you do, you write d. Okay. Okay. Write d matrix, state matrix is equal to, write A x plus b u. Okay. Okay. Here state model, we have state vector, two variables are there, x1 x2, x1 x2. We have only one input, that is f of t. Okay, right. Now look at the right hand side. We do not have x1 coefficient, that's why I write 0. We have x2 coefficient, that is 1. Here x1 coefficient is minus k by m. X2 coefficient is minus f by m. There is no f of t coefficient, so 0. Here f of t is 1 by m. Okay, that's how we have got this. Now capital Y output vector, in this case my output is y. So I should write y is equal to C transpose x. X means I have x1 and x2. Y is nothing but x1. So x1 coefficient is 1, x2 coefficient is 0. So you have got the state model. So the D matrix is 0 here. Okay, that is how you have to write the state model. So I have given three state equations now. Just learn how to draw the state model. So dx is equal to ax plus bu, d x1, x2, x3, fine. A x1, x2, x3 plus b u. There are two inputs, u1 and u2. Now x1 coefficient is 7, x2 coefficient is 3. There is no x3, so 0. Second equation, x1 is not there, x2 is 4, x3 is not there. Third, x1 is 0, x2 is 3, x3 is 0. Come to this one. u1 is 1, u2 is not there. u1 is 2, u2 is 1. Coefficient. u1 is not there, u2 is 1. That's how we get the state model. Right. A control system is characterized by the differential equation y triple dot 6y double dot 11y dot plus 6y is equal to 6u, where y is the output and u is the input. Obtain the state space representation of the system. It's a third order differential equation. I have to get 3 state equations first. Okay. Oh. Okay, state equations. So here y triple dot 6y double dot 11y dot plus 6y is equal to 6u. I will take y is equal to x1 as one state equation, state variable. Y dot is equal to x2, second state variable. Y double dot is equal to x3. Y double dot. One order less than the original one. x3. Third order equation, that's why I have chosen 3 state variables. Now you take this one, convert into state equation. Y dot equal to x2, so this will become dx1 equal to x2. Next, y double dot equal to x3, you can write this way, then d by dt, dy by dt, dy dot, y dot is nothing but x2. So you got second equation. Now y triple dot, transfer everything to the right hand side. So by d by dt of y double dot 6y 11y dot, I can write y double dot is nothing but x3. Then I get the third state equation. Once you have state equation, as I explained earlier, get the state model. Okay. X means x1, x2, x3. x1, x2, x3. There is only one input. That's why u. First equation, x1 coefficient is 0, x2 coefficient is 1, x3 is not there. Second equation, x1 is 0, x2 is 0, x3 is 1. Third equation, x1 is minus 6, minus 11, minus 6. No u in the first equation, no u in the second equation, third equation 6. That's how you get this. And y is equal to small y, that is x1, y equal to ctx, I should write. X is x1, x2, x3, so 1, 0, 0. So we'll get the output equation. Good. Obtain the state space control system, state space or state model of the control system of armature control DC motor. So I have not drawn here because I have been using this quite often. Earlier also I have derived this equation. So that's why I have straight away written down the equations. Otherwise, you just refer the PDF notes and get it. I'll replace EB by KB d theta by dt. I'll get that equation. T I replace by KIA. I'll get this equation. You can observe here, this is a first order differential equation. This is second order differential equation. This is already there. That means there should be 2 state variables for this, 1 state variable for this. There should be 3 state variables for the system. That's why I have taken theta equal to x1, theta dot is equal to x2, IA equal to x3. Now theta dot equal to x2, if I take d theta by dt x2, so d theta x2, you got this equation. Go to this d square theta by dt square. Correct. This equation here. Now write the state equation for this. So you'll get the second state equation. Go to the first differential equation. You will get this state equation. Now you can write the state model. You got the three state equations. Now you can get the state model. Right? That's it. Very simple. Output of the system is y equal to theta. Theta is x1. You have to write y equals c transpose x. Then x is x1, x2, x3. So 1, 0, 0, 0. You got it. Now you can see this system I have given. You have to write two differential equation, one with respect to this mass, other one with respect to this mass. So I have taught you already such problems. Correct? So it's not clear. I can write once again if you want. I can write m1 x1 x double dot plus, you can see here there is one damper. Here you will get x and y. So let me write b2 x dot is equal to b2 y dot. Okay, right? Then here k1 and k1 by 2, k1 by 2 means it will become k1 x k1 plus k2x you get. Along with that, you will get k2y. This is one equation you get. Other equation you get is m2 y double dot plus f of t I should get here. Okay, m2 y double dot plus b2 y dot plus k2y is equal to b2 x dot plus k2x. Okay, like this. So now this is a second order differential equation. X equal to x1 and x dot equal to x2. There are two state variables for this. For the second equation, y equal to x3, y dot equal to x4, another two state variables. Totally, there are four state variables. So now you have to write the state equations. That is pretty easy. Correct? And organize those state equations, then write the state model. You are going to get the state model. Okay? Right. No problem. Take your pen and pencil and paper and you can really do it. It is not difficult at all. Correct. So this is the first equation. This is the second equation. This is the third equation. This is the fourth equation. Now suppose you want to find a system response for this, any one of that kind of problem. This is matrix A, this is matrix B, matrix C, matrix D. Here there are unknown systems, unknown values. So I have given the values for those unknown things here. Then simply say state space A comma B comma C, A comma B comma C comma D. Simply say step sys, step input. It will give you the response, time response. Okay. So once you have the state model, easily we can obtain the response using MATLAB. Okay. So now you have learnt state variables, state vector, state model, and once a differential equation is given, how to convert this into a state model, or once a physical system is given, how to write the equation and convert that into a state model. These things you have learned. Very good. Now let us call Bush form of matrix equation. You see here, I have taken an equation y triple dot plus 6y double dot 11y dot plus 6y is equal to 6u. Form the state model, state equations, then form the state model. This is what you get. This is the diagonal of the matrix. This is what you call it as upper of diagonal, upper of diagonal. So in the speciality of this matrix is upper of diagonal elements remain 1. Last row elements are negative quotients of this differential equation, and all other elements are 0. If a matrix is in this form, we call that form as Bush form. Bush form. Right. When matrix A is in Bush form, matrix B will be all the element except the last one are 0. Okay, right. When matrix A is in Bush form, the state variables, they are also called as phase variables. Okay, right, sir. How to obtain transfer function from state model if you want that on inverse. So ax dot is equal to ax plus bu, y equal to ctx. Since it is a linear system, I not consider d at all, like in this problem. Now if I take Laplace, this will become as x of s is equal to ax of s plus bu of s. Then I have subtract, I'll push this x of s this way, input. Then x of s, when I take, it will become s minus a. So what I do is, this is a matrix, it's an element. To convert that into matrix, I'll multiply by identity or unity matrix. Okay, that is 1 0 0 1. Right, then x of s is equal to si minus a inverse bu of s. Inverse of a matrix is its adjoint by its determinant bu of s. So y of s is equal to c transpose x of s. So x of s is nothing but y of s by ct. So let me substitute here. Y of s by ct will get this. Transfer function is nothing but y of s by u of s. This is what you get. This is transfer function. With the state model is given, you can find the transfer function. Suppose matrix A is given as A, B, C, D. Adjoint is, just interchange these two elements. Push D to A to D. For the other two diagonal elements, just introduce negative sign. We'll get adjoint. For a 3 into 3 matrix, you have to follow how to find adjoint of a matrix. You have to learn that. Determinant of A is nothing but AD minus BC. Okay, that's fine. For a 2 into 2 matrix, it's all right. 3 into 3, you should learn how to find adjoint. I think you know how to find determinant for that. Correct. Suppose this is the state model given to you. So we have A matrix, B matrix, and C transpose matrix. Transpose because I write it in a row form. That's the thing. Okay. Now we have to find Y of S by U of S. Anyway, C transpose is already available to me. I have to first find Si minus A matrix. Si minus A. Si minus A matrix. I will get this. S 0, 0 S, then subtract, you will get this. Adjoint, as I said, interchange, put my negative sign. Determinant is this into this minus of this. You will get this. Now you know all this. Substitute. Multiply. Multiply first. So here it is 1 row and 2 columns. Here 2 rows, 2 columns. 2 rows, 1 column. You can multiply these two because these two are equal. Then you will get 2 into 1. So 1 into 2 into 2 into 1. So 1. So you will get this. Okay. Now state model from transfer function. Suppose transfer function is given, how do you get the state model? Cross multiply, then reverse of that, you write S square Y of S, assuming no initial conditions to be 0, means Y double dot, this should become Y dot Y to U. So once you have got the differential equation, writing the state model is not at all difficult. It is a straight method. Okay. Next, you consider in a state model dx is equal to ax plus bu. If matrix A is diagonal, then that state model is known as canonical state model. So let us convert this into canonical state model. So factorize this. One of the factor is s equal to minus 1, then it will become 0. So you divide this by s plus 1, you will get this. Again, split that into factors. You will get like this. So I can write this as a by s plus 1, b by s plus 2, c by s plus 3. Then comparing coefficients, you have to find a, b, c. I have got a equal to 3, b equal to minus 6 and c equal to 3. Then y of s is equal to, you can write 3u of s plus s plus 1 minus 6u of s by s plus 2 plus 3u of s by s plus 3. This you call it as x1, this you call it as x2, this you call it as x3. So take each one of them. x1 of s equal to 3u of s by s plus 1, cross multiply, get the state equation then in a reverse manner. Same x2 of s equal to this, you take, cross multiply, then write in the reverse, you will get the state equation. Same also for the other. Then you got it, all the three state equation. Then write the state model. Observe in the state model, all the diagonal elements are only diagonal elements are present. All other elements are 0. This we call it as canonical state model. So y is equal to x1 plus x2 plus x3 C transpose x. If I write, I'll get this one. Okay, right, sir. Good. Next, controllability and observability. What we mean by controllability? A system is said to be completely state controllable if it is possible to bring the system from any initial state x of t naught to any other desired state x of tf with the specified time interval. Then such a system is called as controllable. There is a lot of theory behind it. Okay, we have many methods to test also. I'll just take at this level a Kalman's test is sufficient, right? So how do we check whether a given system is controllable or not? So what you do is you need to create a composite matrix QC, that is B, AB, A squared B, like this, A n to the power of n minus B. And the rank of this matrix is n, then it is completely state controllable. That means, how do you do that? Find determinant QC. If this is equal to 0, not controllable. Not equal to 0, it is controllable. Then it has a rank. Okay. Same way you want to find observability, means you observe the output and you should be able to find the initial state. For that again, Kalman's test is there. So QC is equal to C dash transpose, that transpose matrix again, right? Take the transpose of that. Sorry. C dash T, A dash C dash T, like this, and you form this matrix. And the rank of that matrix is n, then it is observable. Not equal to n, not observable. Okay. So dash means it is transpose. That's all the thing. So I'll give this example now. Let us check whether it is controllable and observable. So you have to form the composite matrix B, A, B, A squared B. You know matrix B is 0, 0, 2. AB is A matrix is there, B matrix multiply, you will get this. A squared B means A into AB. So AB already available, multiply, you will get this. Then you get the composite matrix. Okay, 0, 0, 2, 0, 2 minus 12, 2 minus 12, 50. And you find out its determinant. Found to be minus 8. It is not equal to 0, so simply its rank is n, that is rank is 3, is completely state controllable. Whether it is observable or not. Okay. So transpose, already CT was there. Dash means transpose 4, 5, 1. Similarly, A matrix transpose it is. Change the rows into columns. Get this. You will get it. Then you get this. You will get this one. Then again form the composite matrix and find its determinant. Okay. So determinant QC is equal to 0. So system is not observable. Okay. Good. It is quite involved. I think at the undergraduate level, we have decided this much is sufficient. That's the reason not I'm delving very deep into it. Okay. Now suppose state equations are there. How to solve the state equations? Solution of state equations. So x dot is equal to ax plus bu and x of 0 is equal to x naught, that is initial condition is given. It's a first order equation, one initial condition. So if I take Laplace of this will become sx of s minus x of 0 ax of s plus bu of s. So ax of s I'll take it out here, x of 0 I'll bring it up here. Correct. Now it will be like this. So I have multiplied s with identity matrix. Then x of s will be in this form. Okay, let us call this as phi of s. Si minus A inverse, let me call it as phi of s. So x of s, this is phi of s, this is x naught, phi of s, bu of s. Then this will become x of t. X of 0 is nothing but initial condition x naught. This is phi of t. Here you have phi of s, u of s and b. So Laplace inverse of phi of s, b, u of s. There are two functions here. So we know when there are two functions, when you take Laplace inverse, then it will be 0 to t f1 of t minus tau into ft of tau d tau. This is how we write. Again, f1 t minus tau can be written as f1 of t, f1 of minus tau. If that is the case, here phi of t x naught, this I can write, this part I can write integral of 0 to t phi of t, phi of minus tau b u of tau d tau I can write. So take out phi of t, si minus a inverse is constant, so you take out this, then you are left with this. Correct? Then you have to integrate and get the solution. That's all the thing. Now I have given a state model like this. Obtain the response for unit step input. See, what earlier got is complete system response. I'm talking here about for each state you can get the solution. So this is our system and these are the initial conditions given. So in this equation I have to get phi of t. So first phi of s is si minus a inverse, which is nothing but adjoint by its determinant. So I'll get this. Then I have to divide each one of them. I'll get, then I have to integrate. Laplace inverse I have to take. So Laplace inverse of 1 by s minus 1 is e t 0. This is t e t e to the power of t. So I have got phi of t. Phi of minus tau means wherever t is there, you replace with minus tau. Phi of minus tau b u of tau. Okay, this you take. If you multiply, you'll get this. So phi of minus tau b u of tau d tau. So that I have to write. This you have got. Now integrate this part. Also integrate, you will get this. So x of t is given as phi of t into initial conditions and this one. So I substituted. Add these two matrices. Then whatever matrix you come, you multiply. You will get the solution. So x of t, that is x1 and x2. x1 is this how varies with respect to time, and x2 is how it varies with respect to time. So we can find the solution. Even if it is nth order, you can do this way. This is the greatest advantage of state space model. However, for a system, if you use Simulink, we can get the solution like this, right? Graphical. So I think that is what about state models, and this is very, very useful. Now, what is the use? Why did you teach all these things, state model? So now later, after completing this course, I would like to demonstrate some control system design examples. Correct? Whatever theory I have taught you so far, I would like to do this. So there are few tutorial problems available which are typical ones from University of Michigan, and I would like to take one or two problems from that, and I would like to demonstrate how exactly you can design control systems so that whatever theory you have learned so far, you will have the clarity on that, and you will be in a position to design control systems when new problems are given, as long as they are LTI systems, and as long as you can develop their mathematical models. Now, thank you very much.